morning, everyone. Welcome to 4451. Good to see all these eager scholars ready to dive into the class. Like I said in my email to all of you, this is my favorite class to teach of all the classes because this is why I'm an aerospace engineer, is jet and rocket propulsion. All right. So now you can take in this class you're going to take all the hard work that you've done as a freshman in calculus and all these 3450 and whatever, and you're going to be able to take all that knowledge and use it to calculate things like thrust from a jet engine or the efficiency of a jet engine, what fraction of the fuel gets converted into thrust, or the specific impulse. At the end, I'm going to give you a homework assignment where you'll calculate the specific impulse of a hydrogen-oxygen rocket. And you're going to know how to do it, right? You're not going to have to look it up. It's all going to be up here. And so anyway, that's why it's a fun class, because it's like you take everything together, and you get to finally apply it to rockets and gas turbines and scramjets and compressors and all that stuff, and make quantitative calculations of how these devices work. So I have here, I'm just going to pull together a couple documents for you all. And is it really hot in here? Yes. Wow. I guess this probably doesn't work, huh? Yeah. So I have two documents that I've uploaded to T-Square. One is just kind of an overview, and the other is the syllabus. Yeah, I guess that's it. And so we can just run through this. So my office is, if you go down one floor, right here, turn right. If you turn right and you go through the door, you'll run straight into Dr. Zinn's office. The next one is Dr. Seitzman's office. The next one's my office. The only complication with that is I actually have two offices. One there and the other off campus, the NAR building right near the combustion lab. And so I spend a lot of time there. And so the best time to catch me face-to-face is immediately after class, because I'll go down there. Otherwise, you can email me and we can correspond electronically. But that's where room 363 is, right there. So my office hours, like I said, is immediately after class or by appointment. And we'll talk about this a little bit more later, but kind of the overall goals of this class is to really be able to take physical concepts, so take fluid mechanics, take thermodynamics, and be able to apply those to chemically reacting systems. Again, whether that's a jet engine, whether that's a chemical rocket, even whether it's a pressure rocket, be able to perform. This is not a detailed cycle class. You can actually take more detailed classes, but be able to do some preliminary cycle design. So you'll be able to calculate thrust or specific fuel consumption. In other words, how much fuel is burned for a given amount of thrust. You'll be able to do that. You'll be able to understand, if the compressor efficiency isn't 85%, but if it's 80%, how will that affect those numbers? You'll be able to understand, for a rocket, if I'm running at 150 atmospheres versus 300 atmosphere chamber pressure, how will that affect specific impulse? These are the kinds of things that you'll be able to do. And then the last thing, so this is kind of number 3 here is sort of a macro view of the world, right? It's kind of treat all the components as black boxes. We're going to have nozzles and combustors and turbines and compressors, and we're just going to say, stuff goes in, magic happens, stuff goes out. That's how we're going to analyze, that's what we're going to do for overall cycle design. But then what we'll do for the last part of the class right here is actually dive into a little bit more detail on those components. We'll talk about what actually happens inside of a combustor, what actually happens inside of a compressor, or a turbine, or inside a nozzle, or inside an inlet, and so forth. So that's basically the goals of the class. The book. Let's see, where's the book? Right here. Hill and Peterson. Who has the book? 2 people? No one else has the book? Is the book not available? What's the matter with the book? Oh, you have it? Okay, good. Glad you have a book. So where'd you get it from? Amazon.com? Okay, all right. Okay, good. You have sources. So get the book, right? So because you have reading to do, right? So please make sure you get the book, and I just want to make sure there wasn't a problem. Let's maybe I'll just run through a couple of quick housekeeping things regarding the classes. So first of all, homeworks. Well, here, the overall breakdown for the classes right here. Homeworks will be nominally 30%, and then you can see that the basically two midterms and a final with escalating importance. And the way I will grade the midterm and the final is I'll calculate your course grade 3 ways, whereby I'll basically jockey up and down the percentage of each of those by 5%. I'll grab your highest. So in other words, this could be, your course grade could be based on this percentages, or this could be 10% and that 35%, or that 10% and that 30%, whatever. Whichever one gives you the highest grade. And the homework is nominally a third. The way I handle this is usually the idea of the quizzes in the final is really to emphasize your understanding of physics. So I'm going to ask you a lot of questions. You'll have to do calculations. You'll do that, but it's not going to be. It's going to have a lot of qualitative questions. Things like, if combustor chamber pressure goes up, will the specific impulse of a hydrogen oxygen rocket go up, down, stay the same, or not enough info to answer? You know, that would be a pretty typical kind of question. And I'll give you guys copies of the midterms before we have them. But really, the idea here is to emphasize understanding of physics and basically conceptual trends. And this is becoming, in your ability to understand that kind of stuff is becoming increasingly important, because a lot of the stuff that we're going to do in this class, there are tools out there where you can treat those tools as black boxes. You don't have to know anything about, you can go online and find gas turbine cycle design tools, and you don't have to know anything about what happens inside of a gas turbine, and you can do calculations. But it's really, really important that you have some idea of how to estimate and how to expect what the answer should be. Because otherwise, if you don't, then you have no stupid checker, right? Sometimes computers spit out dumb things, or sometimes you put the wrong thing in, or you set it up wrong, and you have to know kind of generally what's going to happen. What should the answer be? Or if this goes up, if my input goes up, should the output go up or down, or not change, or should it go up or down a lot, or should it be relatively insensitive to it? And so the overall philosophy of the midterm and the final is really conceptual understanding. The homework assignments, the objective there is different. It's actually execution of problems. Hopefully, you're going to be busy, and it's only after the class you're going to appreciate how much fun you had doing the homeworks. But they will be interesting, because like I said, you're going to, from first principles, do a lot of the stuff that you've never been able to do before. But the idea there is to satisfactorily carry out the calculation from start to finish. And you'll have nominally about 6 of them. In fact, we should this week I'll be putting the first homework up. Now, just a couple quick things about homeworks. So homeworks are due the morning they're due. I don't take homeworks late, so just have it in time. The other thing about homework is that I don't give partial credit for homework. So that is always a matter of a lot of discussion between people who take my classes and me about homework, but I will tell you why I don't give partial credit, and that is that for a test you have time to do a calc. You have time. You don't have time. Excuse me. There's time pressure, and the idea is that if you're doing a calculation, you add instead of subtract, but you basically knew what you're doing. That's fine. For the homework, you have time to check yourself, and I expect you to check yourself. When you graduate from here and you go design a Mars lander and you mix up English and metric units and you crash the lander, your boss is not going to give you partial credit for getting the answer 100% right other than forgetting to multiply by 3, for completely understanding how to do it, right? So you need to, so there's actually, what you'll find is there's like 2 separate skills involved with doing these problems. One is knowing how to do it. The other is sort of having the discipline to follow it through correctly and know how to check yourself, know how to circle back, particularly if it's a long calculation, kind of being able to put in place the steps that you can check intermediate things. Like, for example, when we do the gas turbine cycle design, you're basically going to be stepping through all the components, and you're going to write a code to do that. And if you're anything like me, there's a 95% chance that you'll have an error in your code the first time, right? Maybe a 99% chance. So you have to know how to go back and say, okay, how do I walk through this thing? So that is a big part of the driver for the homework. So just a reminder, homeworks, I expect them to be done accurately and correctly, and for you to take the time to check yourself to make sure you do it right. Yeah, so I think that's all that I wanted to cover on this overview, and this is on T-squared. Yes, sir?
Just curious about the homework. How long before they're due do you typically post your homeworks?
Usually 2 weeks. Yeah. And one other thing that we need to do is, I think I didn't print it out, but we need to soon enough figure out the midterm dates. And yeah, I didn't bring it with me. We won't do it today, and but we'll set the midterm dates in the next 2 weeks. And so what I'd like for you to do is collect your other midterm dates, and then we can try to adjust the dates so it's not smack on the day that you have 6 other midterms. So there's a little leveling that happens there. But probably we'll do that next week or something, figure that date out. Okay, does anyone else have a question? Okay, well let's talk in a little bit more detail. I want to give you kind of an overview of what we're going to do in the class. This is the outline, and this is also on T-square. So this gives you an overview of what you should be reading, and gives you the page numbers. And we are basically today we're going to be doing 1. We may get to 2A. We may start talking about systems, but and then there's also, in many cases, there's links to slides. These are Professor Seitzman's slides. I will use them, some not exclusively, but I just kept the links there just as an extra supplement. Some of you have pointed out that a couple of the links are broken, and like I said, I think that's because actually the slide may not exist. But like I said, we'll go through some of these. We won't go through all of them, but just as for your reference, they're there. But let's just chat. Let's just walk through this thing. Before we do this, let me just back up and ask a couple quick introductory questions about how this is a propulsion class, and so the idea of propulsion is somehow we're generating thrust to move a spacecraft or an aircraft vehicle. And so I want to just talk for a minute about what's the fundamental mechanism by which you generate thrust. Why do rockets go forward? Why do gas turbines go forward? And let me start by actually thinking about a rocket example. And that is that if you have a jet or a rocket engine, can it exert thrust while discharging into a vacuum? All right. So I have a dead vacuum, no gas molecules. Okay. So I have something that I'm using to accelerate flow, and it's coming out the back end of a nozzle at high velocity into a pure vacuum. Will that generate thrust? Yeah. It will generate thrust. And why? Yeah, it's basically the reason things generate thrust is not because there's molecules that the gases are hitting when they come out of the exhaust, right? Which, if you know the history of the question that I just asked you, you'll know that was actually, there was an editorial in a famous newspaper in the U.S. in the early days of the rocket program saying that the rockets wouldn't work because there was no molecules for the gases to condense with. In retrospect, it seems a little bit obvious, but let's think about it. So we just said Newton's second law is why we get thrust. So that is force equals mass times acceleration, right? So we have a couple of really, really good examples of how this happens. And so maybe I can think about suppose I'm in a canoe sitting on a lake, and I have the canoe full of tennis balls. All right. And so I pick up a tennis ball and I throw it straight behind me. Will that generate thrust? Will that propel my canoe?
A little bit.
Well, for me it will, because I have a good fastball. So what's the mechanism? What's the mechanism for thrust in that case? Yes?
Conservation momentum.
Yep, and so what's happening?
You're creating momentum on the ball in that direction by giving it velocity, so you have to go the other way.
Yeah, I mean, it just goes back to force is mass times acceleration, right? That basically, in order for me to accelerate that ball, I have to exert, I'm putting a force on that tennis ball equal to its mass times its acceleration. I'm sitting in that canoe, and therefore, it's putting a force basically back on that canoe and its propulsion, right? So that is a potential watercraft acceleration device, right? Filling a canoe with balls. Now, what if I, what happens if I have a 20-mile versus a 60-mile versus a 200-mile-an-hour fastball? What difference would that make in terms of the thrust? Yes?
I mean, the faster the ball goes, the larger the original one is, and therefore the larger well, it has to conserve the momentum by exchanging it with the boat. So if you release the 200 mile an hour, then the ball is much larger, produces larger active force.
Yep. Yeah. I mean, and I would have had to. I mean, just going back to F equals ma, right? It's starting with 0. There's clearly a higher acceleration going from 0 to 200 miles an hour than 0 to 20 miles an hour. So if I double the speed with which I'm throwing those tennis balls, I'm going to roughly double the amount of thrust that I generate on my canoe. So that's actually what I just said. Is that example is basically what a rocket does, right? A rocket carries its propulsion, its propulsive matter, and it accelerates it. It accelerates it relative to the rocket. Let's think about another example now. Let's say I have I'm in a canoe, but I'm not carrying any tennis balls. There's somebody on the dock, and they're throwing to me. I'm catching them, and I'm turning around and throwing them. Okay? Everybody get the illustration? I'm going to add one more layer to this. Here's my canoe. Here's the dock. Here's a pile of tennis balls. Somebody throws them to me, I turn around and I throw them that way. Okay. So will that generate thrust? Depends. Okay. There's a qualifier here. What's the qualifier?
How fast are you catching them? How fast are you throwing them?
Yep. Yeah. Exactly. All right. So if this person, and specifically, which way does it go? Let me ask one more question. So, well, let's just go through it. So if this person's throwing to me at 60 miles an hour, and then I throw it out the back at 60 miles an hour, what happens? Nothing, right? So what basically happens is that there's no net effect, right? So they throw me the ball, I catch it 60 miles an hour. Well, that generates thrust, but it generates it in the opposite direction, right? I start accelerating in the opposite direction. Then I turn around and I throw the ball 60 miles an hour, and then I basically cancel it out, and so there's no net. The canoe would basically come to a stop. And so this is actually what is happening in an air breathing device, right? Is that in an air breathing device, you're not carrying the mass along with you, but the key part of generating thrust is that you have to accelerate the mass with respect to your flight vehicle. So now, however, if somebody were just to underhand a tennis ball to me at 5 miles an hour, I catch it, I throw it out the back at 200 miles an hour, I would absolutely generate thrust, right? And so in that case, the amount of thrust that I generate on the canoe would be directly proportional to the delta in velocity of the tennis ball. The bigger the delta of the velocity, the more thrust, right? As well as if somebody was throwing medicine balls to me, right? So there's the delta U, and then there's also the sort of the m dot part, right? So if somebody's throwing me tennis balls, and I'm turning and I'm throwing them, versus somebody throws a medicine ball at me at 5 miles an hour, and then I turn around and throw it at 200 miles an hour. I would get a whole lot more thrust, right? Because as we're going to talk about, thrust is directly proportional to, for an air-breathing device, m dot times delta U, right? The mass flow rate through your propulsive device times the change in velocity. And we're going to talk about this in a whole bunch of different ways. For air-breathing devices, there's 2 ways that you can generate thrust, right? One is m dot, the other is delta U. And they're not the same thing. So, in other words, you can have a very, very large mass flow rate through a jet engine and a small delta U. In other words, just give it a little bit of an increment in velocity. Or you can have a small m dot with a really big delta U, so you really accelerate the flow, and you can generate the same amount of thrust. So which one's better? Anybody know? Yeah, it just depends what you want. It depends what your definition of better is. If your answer is fuel economy, the first one's better, right? If your answer is thrust per unit weight of engine, the second one would be better. It just depends what you want. So you have to be, and we're going to talk about this. We'll talk about the metrics by which we calculate engine performance. And this actually goes to an example, this specific question goes to something that we're going to talk a lot about with air-breathing devices, is there is always a trade-off between the efficiency with which you can convert energy into thrust, for example, fuel into thrust, and the energy density of your propulsive device. So the example we just gave, I just said that you can do things, we'll talk about this. So thrust, we're going to call that T, is going to be m dot times U exit minus U, where U is your the speed into your jet engine. So as we said, there's 2 ways you can do it. So if you think about it, m dot is somewhat like the size of your engine, right? So if you have a great big high bypass ratio turbofan, you're going to get an m dot because you got so much frontal area through that thing, and so, but yet just because the engine's that much bigger, it's going to weigh more. Whereas if you have a much smaller diameter engine with a smaller area, you'll have a lower m dot, but to get the same thrust, you need a bigger delta U. But what we'll talk about is the specific fuel consumption is the thrust per amount of fuel burned. The way to optimize that is to drive this down, drive that up. Whereas power density is something which you might care about, and that might be something that you would want, say, for a civilian application where you're trying to minimize fuel burn, right? I mean, Delta Airlines spends hundreds of millions of dollars a year on fuel prices, and so if you can bring your fuel economy up by a couple percentage points, that can be easily millions or even tens of millions of dollars in fuel savings. Whereas, you don't necessarily care about fuel economy, you just want to go fast and you want to have a small, really light engine, like you might for a military application, then you're going to probably be pushing more on that power in order to get delta U. But we're going to talk about, we're going to put the equations down and we'll get into that a little bit more. I just wanted to overview that. Now, does anyone have a question about that? Yes, sir. Let me ask you another question. And I'm going to go to a rocket example. Looks like a fish. It's supposed to be a rocket. Okay, so this rocket is going at 20,000 miles per hour. All right. I have some exit velocity of the gas that's coming out of this rocket, okay? I'll call that UE. And this will be the exit velocity with respect to the rocket, okay? What does UE have to be in order to generate thrust?
That's zero.
You guys are all so good. Yeah, you nailed it. All right. Exactly. Anything, right? It can be 0.01 miles per hour, and you will generate thrust. Right? And so this goes back to my canoe example. If I'm in my canoe and I'm going 20,000 miles an hour across the lake in my canoe, I can throw that tennis ball at any speed and I'll generate thrust, right? I mean, I can just throw them out at 1 mile an hour, right? And I'll generate thrust, right? The key point here is that this is UE with respect to the rocket, right? So with respect to a stationary observer, it would be very, very different than 20,000 miles per hour. It would be very different than that number. But the point is I'm accelerating mass with respect to the rocket. Now, yeah, that was the point I wanted to make, and we shot through that one. That was easy. That usually throws people off. Oftentimes people say, oh, it has to be 20,001 miles per hour. That's not true. Anything you do will generate thrust. Okay, well let's do a quick class overview here, and I'll refer to this just to give you an overview of what we're going to do starting on Wednesday. What we're going to start out with is a refresher of thermodynamics. Okay, so think 3450. We're going to go into a little bit more detail. In particular, we're going to do something which you didn't do in thermo, which is to consider chemically reacting, thermodynamics and chemically reacting flows. So in flows where the chemical composition of your gases is changing. Anybody have any ideas why I would care about that? Yes?
For propellants and how the momentum changes when you light them on fire.
Yeah, so combustion, right? I mean, you're burning stuff. You're going with fuel, let's say rocket propellant and oxygen, or hydrogen and oxygen, and it's changing into water. Or if it's jet fuel, you have some hydrocarbon getting converted into carbon dioxide and water. So combustion is one example where we're absolutely going to have to think about changes in chemical composition. Does anybody have any other ideas on why we might care about that for this class? Well, it turns out that actually, particularly in rocket type applications, or scramjet type applications, when you have such high temperatures of the gases, that you actually can have changes in composition as the gas is flowing. So we'll get into this when we talk about rocket nozzles. And you'll hear the word nozzle chemistry. You might not realize it, but actually, even after the combustion reaction nominally is completed, the composition of the gases can be changing as the gas is flowing through the rocket, through the nozzle, because the pressure and temperature is changing. A simple way to think about that might be that if you think about, say, oxygen, at low temperatures, oxygen likes to be O2. Does anybody know what oxygen likes to be at really high temperatures?
No.
O, right? It dissociates into O. Exactly. So you have in rocket type applications, you oftentimes have lots and lots of dissociation where the O2s become O's, or the products of combustion, maybe water. H2, rather than being H2O, it becomes H's and O's and things like that, just because the water at 4,000 degrees K, for instance, water doesn't want to stay water, it wants to be something else. But yet, as it's flowing through the nozzle, it's expanding, the temperature's dropping, so you're getting recombination reactions. And so nozzle chemistry is another important example where we have to think about chemically reacting flows. So that will be, so you can see as we talk about this part here, Roman numeral 2 is our refresher of thermo. A, B, C, and D will be a review of things you've done before. E, equilibrium chemical thermodynamics, will be new. And what we're going to need to do basically is to generalize your understanding of enthalpy. So if you remember the energy equation from 3450. Can anybody summarize what the energy equation says? Steady state energy equation. It's you don't need to say but just in words, physically. Yes?
Energy can be neither created nor destroyed. Delta equals 0.
Yeah, yep. And so from a control volume point of view, do you remember how that works for like a 1D flow? Stuff's flowing in, stuff's flowing out.
What goes in must come out.
Pardon?
What goes in must come out, unless there's a change.
Yeah, so you're basically saying I have some stagnation enthalpy flux coming in. I have a stagnation enthalpy flux coming out. Stuff's coming in. So you use H naught or HT for stagnation quantities. H naught, right? So you have some stagnation enthalpy coming in, remember, which is H plus U squared, over 2. So you have some flux of stagnation enthalpy coming in. You have some flux of stagnation enthalpy coming out. Are they the same? They're not necessarily the same. What would make them different? Work, if work has been done, or if heat has been added, right, or taken away. Yep. So the difference between stagnation enthalpy in and out is proportional to Q dot minus W dot. So what we're going to do here for this part is we're actually going to generalize that, and it's actually quite intuitive, because in addition to basically the internal energy, if you remember, H for a perfect gas is directly proportional to temperature. So this is basically temperature. So what we'll do here is we'll also have chemical energy. So it's a relatively, I think from a conceptual point of view, it's pretty straightforward, the generalization. It gets a little bit messy sometimes when you work through the details, but that's why it's important to understand what you're doing and then dive down into the calculation. But basically, we're just generalizing the enthalpy to include both also internal energy associated with chemical bonds, not just due to the temperature of the gas. Okay, so that's what we'll do in 2. Then what we'll do is we'll spend, so that will take, I don't know, first quarter of the class-ish, something like that. So look at the schedule. What we'll do next is we'll do air breathing systems. And that's 3. And we'll start by looking at some basic performance parameters. So how do we, this goes to the question that I asked over here, and I said, which way is better, more M dot or more delta U? And the answer came back, it depends. So in order to evaluate propulsion systems, we're going to need some performance parameters. We're really going to focus on 2 critical ones. And those 2 critical ones you can sort of think of as like miles per gallon, or fuel efficiency, what's called specific fuel consumption. That'll be one. Is just how much shaft work, if it's a turboprop or a power producing gas turbine, how much work do you get out, useful work out do you get for a given amount of heat release from fuel. That'll be one performance parameter, and the other will be basically an energy density performance parameter. How big does your propulsor or your power plant have to be in order to get a certain amount of work output out of it? Or if it's a flight vehicle, how big does your engine have to be in order to get a given amount of thrust? If you work for Boeing or Airbus and you say I need a 100,000 pound thrust class engine, does the engine have to be that big in diameter or that big, just some basic sizing. And so that fuel economy and energy density metrics, those will be the 2 that we're really going to be focusing on in quantifying performance. So, for example, one of the things that you'll understand very, very well at the end of this class is that fuel economy of a gas turbine engine, in other words, the miles per gallon or the specific thrust, directly goes up with compressor pressure ratio. All right. So, in other words, if you think about a gas turbine, actually, we have minutes for these, don't we? pulling up customer sites notes here just so I have a picture to refer to. That's pretty cool, huh? Okay. Actually, so is that. Anyway, you know, this is a like a turbojet right here, where you have a compressor, a combustor, a turbine. So one of the things you will know by the end of this class is that the higher you can compress the gas going into coming out of the compressor, the better the fuel economy of the cycle will be. And so that kind of helps you understand immediately why. Does anybody know the pressure ratio of a modern aircraft engine? It's about 55. Okay, so you know the like the GE Gen X engine for the Boeing 787. It's about 55. So 55 times 14.7. What's that? Well, 50 times 15 is 750. So about 750 psi. Although I like to do my calculations in metric. I think in English. I don't know if you guys are fully transitioned over to metric or anyway. So 750 psi is the pressure coming out of that compressor. And so a modern aircraft engine is a pressure vessel. It's a flying pressure vessel because it is 750 psi in there, and in this section right here, it's really hot. So the reason it's a flying pressure vessel is because you get more fuel economy as you go up the pressure ratio. And what they're talking about, in fact, is pressure ratios, you know, looking forward of 70, which is pretty awesome. Some of you will get to work on those. Compressor pressure ratios of 70. And what that also means is that the cold gas coming out of the compressor at station 3 is not so cold. It can be 1400 F even before it goes into the combustor. Because if you remember from thermo, when you compress a gas isentropically, its temperature goes up, right? And that introduces all kinds of design challenges. So for example, I do combustion. That's my field. And one of the interesting challenges that GE had when they developed the Gen X engine is it's not only really high, it has really great fuel economy because it has that high pressure ratio. It's also really, really clean. It emits very, very few pollutants, NOx, nitrous oxides, which give you smog. But one of the big challenges they had with that system was, in order to make the combustor work, is you have to take the fuel in the air and you have to mix them very, very well before they burn. That's called a premixed combustor. And we'll get into what premixed combustors are later. However, what you're doing is you're taking jet fuel, and I'll give you a number. Jet fuel auto-ignites at around 400 degrees Fahrenheit. Okay, so if you take jet fuel, mix it with air, heat it up to about 400, bang, it'll spontaneously go kaboom, right? Below that, it won't, right? Which is why, like, in my garage at home, I have a tank of gas. I'm not worried about my garage burning down because gasoline and air, unless you have a spark at ambient temperature, it won't auto-ignite. But if I were to take that gasoline and air and heat it up to above around 400, it would burn. So, does anybody see what the challenge might be here? Is that you have to premix the fuel in the air. But what does the fuel want to do? It wants to burn, right? It's thinking, okay, it's above 400. Not only is it above 400, it's 1400, and you're telling me not to burn. You're telling me just to uniformly mix with the fuel and air. So anyway, that was a big challenge with the development of that engine, was dealing with that particular issue, which was auto-ignition, having the fuel in the air prematurely burn, which by the way then counteracts the low pollutant performance of the device. That if the fuel in the air burned without thoroughly mixing, you make a lot of smoke, producing gases, NOx. Okay, anyway, the reason I brought that up though was because I was talking about performance parameters and specific fuel consumption. And I had said that by the time you leave this class, you will thoroughly understand the effect of pressure ratio, for example, on fuel consumption. On the other hand, I'll give you the other parameter is that energy density. We're going to call it specific thrust for propulsive devices. Specific thrust is the amount of thrust you get out of the device normalized by the mass flow rate through it. All right, so if you have a high specific thrust, you're going to get lots and lots of thrust for relatively little mass flow rate. So again, and if you think about mass flow rate as that's basically an indicator of the size of your power plant. Well, the single biggest parameter affecting specific thrust is turbine inlet temperature. All right, so if we go back to this picture, and again, we're going to get into all this. The temperature at station 4 is high. If you can make that higher, you can get more specific. You can get more thrust for a smaller amount of MDOT. So what do you think? What do you think that might design decisions that might drive, or what? And also, what kind of design challenges? Yes.
You gotta make sure the materials that the engine is made of don't melt.
Yeah, exactly. Particularly, remember the turbine is spinning, right? And I don't know if you've heard that the G loading on a turbine blade is equivalent to hanging an SUV off the turbine blade. So lots and lots of G loading, and oh, by the way, the gas temperature is really high. Please don't fail. Right? Please don't fail. Because when these kinds of components fail, really bad things happen. You remember the engine fire in Reno? Happened, what was it, a year or two ago? I don't know if that was a turbine blade failure, but you got stuff spinning really fast, and when it lets go, sometimes it goes through the engine. Most of you won't remember this, but actually there was somebody, a mother and child was killed in Atlanta at Hartsfield when a rotor disc failed on a Delta engine. This was maybe 15, 20 years ago, and it was an uncontained failure. When that disc is so heavy, if it fails, it's not to make anybody nervous about. Although I do, when I sit on a plane, I line myself up with the jet engine. I just think, I don't know. but anyway, but coming back to the turbine, you want the temperature to be as high as possible because that gives you the most, bang for your buck, so to speak. And so, does anybody know what the temperature, a modern turbine inlet temperature might be of a gas turbine? So I just told you pressure ratio is about 55 to 1. Well, let's see. I know it. It's over 2,000 K for a military type application. So over 3,000 degrees Fahrenheit. So what that means is the turbine is seeing temperatures that are above the melting temperature of the material. I don't know if you knew that stat. So this is why people who design turbines are awesome. Because they are actually, the turbine has the G loadings equivalent to hanging an SUV off of it, and the temperature of the gases it's seeing is higher than the melting temperature of the material. So how does that happen? How do you get temperatures higher than melting temperature?
Cool air.
Yeah, cooling. So basically, turbine designers are heat transfer rocket scientists, right? They know heat transfer in and out, and so they basically design these things so there's this shroud of cooling air around it. And if that cooling scheme breaks down, it's game over. That turbine will melt very quickly. But I guess what I'm trying to drive at here is these macro performance parameters: pressure ratio driving fuel efficiency, turbine inlet temperature driving specific thrust. That in turn drives a lot of the really important engineering challenges that we have in making jet engines. We want them to be very high pressure because that increases the fuel economy. We also want to make that turbine able to withstand as high a temperature as possible because I'm going to be able to get more thrust out of my device for a smaller device. There you go. So that's performance parameters. We come back to this. That's what I have here. Then what we're going to do is we're just going to basically walk through, starting with ramjets. Ramjets are the simplest because they don't have a compressor. All the compression happens through ram compression. And then we'll do turbojets. Then we'll do turbo fans. And that'll basically be it for air breathing devices. Then we'll go over to rocket propulsion systems. And we're going to consider both chemical rockets and electrical rockets. What time are we done? 9:05. Okay. So we're going to look at both chemical rockets and electrical rockets. And I got 2 minutes. So what's the fundamental difference between a chemical rocket and an electrical rocket?
You're carrying your oxide with you.
Yep. And one of the big differences that we'll get to in a chemical rocket, the oomph to the, let's say, a hydrogen-oxygen system. There's a certain amount of chemical energy in the hydrogen-oxygen system. That's also the stuff that's getting accelerated. In an electrical rocket, you decouple the energy source from the propellant, right? So hydrogen-oxygen system, there's a certain ISP that you can get, and that's what you get. I forgot the number, 300-something seconds, right? In an electric rocket, you can get any ISP you want. Fundamental difference. When you decouple the propellant, the thing that's getting accelerated from the energy source, it fundamentally changes that. And that's electrical rockets here. I'm almost done. Okay, and then the last topic for the class will be analysis of turbine engine components. So we'll look at inlets, we'll talk about combustors, we'll talk about compressors, turbines, and then we'll be all done. So does anyone have a question? Yes, sir. A little bit, but not too much. Yeah, we're going to cover ramjets.